friends, and welcome to your first lesson in Unit 8, where we're going to be talking all about electrochemistry. So our big focus in this unit is going to be all about electrons.
And that first starts with redox reactions. So redox is just short for oxidation reduction. A redox reaction involves a transfer of electrons between two species. So oxidation itself is loss of electrons, and reduction is gain of electrons. The way I have always been taught to remember it, or the way I remember it, is oil rig. Oxidation is loss, reduction is gain. So oxidation is the process of losing electrons, reduction is gaining electrons. So this is really easy to see for an ionic compound. So sodium, when combining with chlorine, not only produces a big flame, but it involves the transfer of this one sodium electron over to chlorine. Because sodium is losing an electron, it is oxidized, and because chlorine is gaining an electron, it is reduced. Now, this is something where this terminology gets confusing right here. So something is the reducing agent, also known as the reductant, when it provides electrons or reduces something else. So in order to provide electrons for something, it itself is going to lose them. So it is being oxidized, while the oxidizing agent is the thing removing the electrons. So if it is removing electrons from something, it itself is gaining them, so it is reduced. So losing electrons is oxidation, gaining electrons is reduction. In this case, sodium is providing the electrons, so it is the reducing agent. But it's oxidized. While chlorine is the one that's pulling the electrons away or removing it from sodium. So it is the oxidizing agent. I don't really know what word I just wrote there, but it's supposed to be oxidizing. And in the process of being an oxidizing agent, it's reduced. So it's a little confusing, and that's just something you got to kind of go over in your head to make sure you have it down. So redox reactions don't just involve ionic compounds, however. It also involves covalent compounds. But in a covalent compound reaction, instead of electrons being transferred like we saw in the previous slide for an ionic compound, the oxidation number of an atom changes. So what is an oxidation number? Sometimes it's called an oxidation state. We'll use the term oxidation number. But it's a number that is given to an atom in order to see how the electrons move around in a chemical reaction. So the way we give something an oxidation number is we look at an atom within a covalent compound, such as, let's say, water. And we say, okay, if this was ionic, so like if something were to take away electrons and lose electrons, like what happens in an ionic compound, what would the remaining charge be? So we have to think about the electronegativity of atoms involved in the covalent compound, because the ones that are more electronegative are the ones that are going to pull the electrons to it. So you kind of think of this like a tug of war. So in water, we've got two covalent bonds. So in each of these, we've got a hydrogen and an oxygen. So oxygen is much more electronegative than hydrogen. So if we could think of this like a tug of war, oxygen would win, and so these electrons would go to oxygen. Same over here. So if this happened, and oxygen gained those 2 electrons, then oxygen is going to have a -2 oxidation number. Hydrogen lost its electron in the tug of war with oxygen, so now it has a +1. These aren't real charges because, of course, these are covalent compounds. They're actually sharing instead of transferring. But in order to give an atom an oxidation number, we have to think of it like, okay, if this was ionic, who would win the tug of war? How many electrons would they gain overall, or how many would they lose overall? So some simple rules that goes along with this. So an elemental substance is always going to have an oxidation number of 0. So anything in its standard state, like O2, which is diatomic, so O2 is the standard state, that's going to have an oxidation number of 0. It's not gaining, losing electrons. It just has an oxidation state of 0. Like in the previous slide, if it's an ion, the oxidation number is just its charge. So that's super simple. We already know what charges things have, like sodium's +1, magnesium's +2, chlorine's -1, sulfur's -2. Whatever its normal charge is, that's its oxidation number. When hydrogen acts like a metal, when it's combined with a nonmetal, it is always going to be +1 because of the reason I explained over here. So if we look at this example, methane, CH4, carbon is the more electronegative atom. So carbon would be the one that actually won out and got all the electrons. So in this case, hydrogen is going to be +1, and carbon would actually be -4. Now, if hydrogen is acting like a nonmetal and it's paired with a metal, it will be the more electronegative one, and also this is an ionic compound, and so it's just its charge. Lithium is +1 and hydrogen is -1. The oxidation state of oxygen is almost always -2, so that's what we got over here. But every now and again, if it is with fluorine, it's +2, and that's because fluorine is our most electronegative atom, and so fluorine would win in that tug of war, so fluorine would get the electrons and oxygen would be left missing too. Excuse me. If oxygen is in a peroxide, so that's like hydrogen peroxide, it is only actually going to have -1 because this right here is between the same atoms, so they each only get 1. So that gives it an oxidation state of -1. Fluorine, because it is so electronegative, will never ever lose its tug of war, so fluorine will always be -1. So if we've got an ion or a compound, we always need our oxidation numbers to add up to the charge of the ion, so like in this case, or if it is a molecule, we need it to add up to 0 or neutral. So we already did the explanation of water's oxidation state over here. +1, there's 2 of them, -2, that makes 0. For SO4, we've got sulfur with our oxygen. So the oxygen is going to be the more electronegative. And again, unless it's in with fluorine peroxide or superoxide, it's -2. So oxygen in this case is all going to be -2, but there's 4 of them, so that total makes -8. And then sulfur already has 2 electrons on it. It's going to get 1 from each of these bonds, so it's going to be +6. So +6 minus 8 is -2. You can also do this simply by saying, we know oxygen's -2, Negative 2 times 4, total is negative 8. I need this to add up to negative 2, so sulfur has to be plus 6. So let's go through some examples. You can pause if you want to try on your own, or obviously you can listen to me go through it. So for this first one, we have H2S. So in this case, hydrogen is with a nonmetal. So when hydrogen is with a nonmetal, it is plus 1. We have 2 hydrogens, so the total is plus 2. This all together needs to add up to be neutral, so sulfur has to be minus 2. Oxygen is minus 2 times 3 is a total of negative 6. I need this to add up to negative 2, so sulfur has to be plus 4. So obviously, we can see that elements can have different oxidation numbers. Here, sulfur was minus 2, and here it's plus 4. So it totally just depends on what it's bound to and what's going on in the compound. Here, this one's simple because this one's ionic. So sodium's oxidation number is plus 1. There are 2 of them, so altogether that's plus 2. We know that's why sulfur has a negative 2 charge altogether. Oxygen is minus 2 times 4 is negative 8, so sulfur has got to be plus 6 to give me that negative 2 charge overall. Something to point out, the oxidation number of each sodium is plus 1. We just have 2 of them, which gives us that total plus 2. It's no different than charges. Here, hydrogen is with a nonmetal again, so hydrogen is going to be plus 1. We have 4 of them, so carbon has to be minus 4. Nitrogen is in its normal elemental state, so its oxidation number is 0. So because we don't always have this full-on transfer of electrons the way we think about it in an ionic compound, a more general definition of a redox reaction is just a reaction in which the oxidation number of each element changes. So the oxidation number changing would mean it's either going to go up or down. So if something's oxidized, as we said, oxidation is loss. If you lose electrons, you're going to become more positive, so your oxidation number is going to increase. Reduction, on the other hand, reduction is gain. If you gain electrons, you're going to be more negative, so your oxidation number is going to go down. Does not necessarily mean your oxidation number will be negative, it's just going to decrease. So in this example, sodium is in its normal elemental state, so its oxidation number is 0. Chlorine gas, normal elemental standard state, so it is going to also be 0. But over here in sodium chloride, this is ionic, so its oxidation numbers are just its charge, so plus 1 and minus 1. So if we look, sodium went from 0 to plus 1, so it lost an electron, so it was oxidized. Its oxidation number went up. Chlorine went from 0 to negative 1, so it was reduced. Same thing over here. These are both in their natural state, so their oxidation number is 0. Over here, hydrogen is going to be plus 1, chlorine's minus 1, so the same idea. Hydrogen is oxidized and chlorine is reduced. So oftentimes, single replacement reactions are going to be common redox reactions. Something that's good to point out with this reaction right here, so zinc is 0, hydrogen plus 1, chlorine is minus 1. Over on the right-hand side in the products, zinc is now plus 2 because it is with 2 chlorines, and each chlorine is minus 1 times 2 gives me minus 2. So I need plus 2 total. Hydrogen is in its natural state still, so it is 0. So if we look, zinc went from 0 to plus 2, so it is oxidized. Hydrogen went from plus 1 to 0, so it is reduced. Chlorine, negative 1 to negative 1. It was neither oxidized or reduced. So another practice, copper, normal elemental state, oxidation number of 0. This is ionic, so it's just the charge, so silver is +1. Nitrate has to add up to -1, so oxygen is -2 times 3 is -6. We need a total of -1, so the nitrogen is +5. On the product side, copper is now with 2 nitrates, so it has to be +2. Nitrate itself still has a -1 overall charge, so the oxygen is going to be -2 times 3 is -6. For nitrogen then has to be +5. Now silver is in its normal elemental state, and so its oxidation number is 0. So for this problem, copper went from 0 to +2. So copper is oxidized. And then silver went from +1 to 0. So silver was reduced. Both the nitrogens and the oxygens were neither oxidized or reduced. So some more practice. We're just going to identify what species is being oxidized and what species is being reduced. So oxidation is loss, reduction is gain. So right here, chromium is +1. Over here, it's +3. So that would require the loss of electrons. The oxidation number is going up, so it was oxidized. Tin is going from +4 to +2. That means it would have to gain electrons to do that. Its number went down, so it was reduced. Mercury is +2 in the reactants, but over here it is 0 because it's in its standard state. Iron over here, or excuse me, because it went from +2 to 0, it was reduced. Iron goes from 0 to +3. So in order to do that, you would have to lose electrons, so it was oxidized. And now I'm not sure if I said the mercury correctly, but +2 to 0, it would have to gain electrons, so it's reduced. Arsenic over here is in its natural states with 0, as is chlorine, but on the right-hand side, arsenic is +3, so it went from 0 to +3, so it was oxidized. Chlorine went from 0 to -1, so it was reduced. So in order to identify which equations are redox, we have to determine if any oxidation states changed. If no oxidation states changed at all, then that means there's no reduction or oxidation, so it wasn't a redox reaction. So in zinc carbonate, zinc is going to be +2. Carbonate has to add up to -2, so oxygen is -2 times 3 is -6. To leave a leftover charge of -2, that means copper is +4. That looks like a 9. Oops. All right, so on the right-hand side, zinc is still +2. Oxygen is -2. Carbon in carbon dioxide, oxygen is -2, -2, or excuse me, times 2 is -4, so carbon has to be +4. So if we look at this reaction, nothing changed its oxidation state. So this is not a redox reaction. Instead, this is just a decomposition. Down here in B, we have just an element, so it's 0. Bromine in natural state 0. But over here we have +3 and -1. +3 because that's the charge of gallium. So gallium went from 0 to +3, so it was oxidized. Bromine went from 0 to -1, so it was reduced. So this is a redox reaction. Now we have the decomposition of hydrogen peroxide. Because this is a peroxide, oxygen's oxidation number is -1, hydrogen's +1. In water, oxygen is -2 and hydrogen is +1. When it's alone diatomically, its oxidation state of oxygen is 0. So this is an interesting equation because the hydrogen doesn't change at all. But one of these oxygen atoms becomes -2. So -1 to -2 is reduction. But the other oxygen atom went from -1 to 0, so it was actually oxidized. If we look at part D, barium is going to be +2, chlorine -1, +1. Sulfate has to add up to -2, so oxygen's -2 times 4 is -8. So to leave -2 left over, we're going to have +6. Over here, +2, same deal, +6 -2 +1 -1. All of these are ionic. All of them are keeping their charges. So this is not a redox reaction. Sorry, the previous one was. This is a precipitate reaction. Down at the bottom, we have combustion. So here, hydrogen is +1. We have 4 of them, so that's +4 total. Carbon, there's 2 of them, so each of them are going to be -2. Oxygen is in its normal state, so it's 0. In carbon dioxide, we have oxygen -2 times 2 is -4, so carbon is +4. And in water, oxygen's -2, hydrogen is +1. So we looked to see if anything changed, and in fact it did. Carbon went from -2 to +4, so it absolutely was oxidized. And our oxygen, one of our oxygen atoms anyways, went from 0 to multiple oxygen atoms, went from 0 to -2. So each of those were reduced. And sorry, this is getting so messy, but there we go. So this was a redox reaction. So B, C, and E were redox reactions.
Okay, guys, so now we're going to talk about balancing redox reactions. And sometimes it's super simple. It's as much as just balancing a normal reaction where we put our coefficients to make sure that there's the same number of every element in the reactants as there is in the products. But sometimes it gets more complicated than that, and we have to use a method that includes half reactions. And what a half reaction is it's just breaking the redox reaction into its reduction reaction and its oxidation reaction, so splitting those apart. So for this first example, in sodium plus chlorine gas making sodium chloride, we break down the two half reactions, which is the sodium and then the chlorine, and we balance them with the electrons. So we see that for sodium, it is going from 0 to +1, so it lost reactions, or lost electrons, so that's the oxidation reaction. And then chlorine, which went from 0 to -1, gained electrons, or in other words, was reduced. And so we see we have the oxidation reaction and then the reduction reaction. And the electrons are balanced. They always have to be the same because you can't lose or gain more electrons. And so something here that will be good to point out in our half reactions is oxidation is lost, so electrons are always in the products. And for your reduction reaction, electrons are gained, so your electrons are in the reactants. And sometimes that just helps us remember when we're balancing where to put the electrons. Okay, so what are our steps to balance a redox reaction? So the first thing we're going to do is we're going to write those two half reactions. So we're going to break apart the oxidation and the reduction. Then we're going to balance every element present that is not oxygen or hydrogen. So anything else that needs balancing, we're going to balance it with coefficients, just like we always balance equations with coefficients. Then you balance any oxygens by adding water molecules to the other side, right? So H2O So for every oxygen, you're going to add an H2O. Then you're going to have a misbalance usually of hydrogens. So you're going to balance those by adding H plus to the other side. H plus, those come from acids. So that's why these are called balancing them in acidic solution, or in basics, we'll see in a moment, but the steps still start the exact same way. Then we balance our charge by adding electrons. Remember, if it's an oxidation, you add the electrons to the products, and if it's a reduction, you add those electrons in the reactants. But we use those electrons to balance out our charge. Then we're going to add our two half reactions together and cancel out any like terms. You should never have electrons left because, again, the number of electrons has to be the same. You can't gain more than you lost. You can't lose more than you gain. If we're going to go a step further and not leave it in acidic solution, but instead do it in basic, then any hydrogens on one side, you're going to add hydroxide to them because H plus OH creates water. So by adding hydroxide to one side, you convert the hydrogens to water. But what you do to one side, you have to do to the other side, so then you're going to have hydroxides on the other side. Again, you're going to cancel out any common things like hydrogen or water. And so previously in our final balanced reaction, we're going to have H pluses. If we're doing so if we're balancing it in a basic solution, we're going to have excess hydroxides. Okay, so if you like this kind of written out in a textbook style and they give you a nice little diagram, here is how we balance redox in acidic solutions. And then here is basically the exact same set of instructions, right? Because we do it the same way. We just add these steps right here where we convert any H pluses into water by adding hydroxide. So let's go through one guided example before we try some on our own. So we're balancing this reaction. So the first thing that we're going to do is we're going to separate it into its two half reactions. So we have this reaction and this reaction. So I've separated them out into the two half reactions. So now we're going to balance everything that's not hydrogen or oxygen. Well, we have one iron and one iron, so those are already balanced. Now I have two chromiums here and only one over here, so I've got to add a 2 in front of that chromium. Now I'm going to balance any oxygen atoms with water. Now I don't have any oxygen in the iron half reaction, but in the other one I have 7. So I've got to add 7 waters on the right-hand side. Well, now that I've added 7 waters, I have 14 hydrogens on the right. So I have to balance that by adding 14 hydrogens on the left. Now we have our two half reactions. We need to add in our electrons. So for the iron reaction, we have a +2 on the left and a +3 on the right. That is an oxidation reaction because we're losing electrons, so the electron has to go in the products. But then that also makes sense because in order to balance this, +2 and +3, when you add in that electron, now my charge on the right is +2, my charge are balanced. On the left-hand side, my charge is -2 plus 14, which is a total of -12. On the right-hand side, I have 2 times +3, which is +6. So how can I make, oh, I'm sorry, not -12. 14 minus 2 is +12. So how can I make +12 equal +6? I add 6 electrons. And again, this is the reduction reaction, so it makes sense the electrons are in the reactants. Okay, so I have 6 electrons here, and I only have 1 there. Well, that doesn't add up. So I got to multiply the first reaction by 6 so that my electrons will cancel. So now here are my fully balanced half reactions. I'm going to cancel out any like terms. So the 6 electrons are going to cancel out. And then I combine my two half reactions to get my full balanced reaction there. Okay, so let's do this reaction. We're balancing it in acidic solution. So my half reactions are going to be Fe2O3 to Fe. and then I have CO to CO2. So those are my two half reactions. Now I'm going to balance anything that's not oxygen or hydrogen. So I have 2 irons on the left, but only 1 on the right, so I'm going to add a 2. Down here, both my carbons are balanced. So now I'm going to balance oxygen with water. So I have 3 oxygens on the left, so I'm going to add 3 waters on the right. Down here, I have 1 oxygen on the left, 2 on the right, so I need to add a water to balance out the oxygens. Now that I have 6 hydrogens on the right-hand side, I got to balance that with 6 hydrogens on the left-hand side. Down the second reaction, I have 2 hydrogens on the left, so I need to balance that with 2 hydrogens on the right. Now I need to balance my charges. On the left-hand side, I have 6 plus and 0, so I'm going to have to add 6 electrons over here to balance that out. In the bottom reaction, I have 0 on the left and a +2 charge on the right, so I'm going to add 2 electrons to balance that out. Okay, so now my electrons need to match. So I have 6 in the top reaction, but only 2 in the bottom, so I've got to multiply through this whole reaction by 6. So that gives me 6 waters, 6 carbon monoxides, 6 carbon dioxide, and oh, not 6. What am, y'all? I'm losing it. I'm really losing it. In order to be 6, we got to multiply by 3, which gives me 3, 3, 3. 3 times 2 is 6. 3 times 2 is 6. Whew. Okay. Now I'm going to cancel out any like terms. So 3 waters, 3 waters. I have 6 H pluses, 6 H pluses. Electrons have to cancel. If they don't, we've done something wrong. Now I'm going to add up what I have left. And in this one, we actually canceled out all of our additions. And this is our final balanced equation. All right, this one says in acidic solution, hydrogen peroxide reacts with iron 2 plus to form iron 3 plus and water. So first I'm going to write my equation. All right, so now I'm going to do the half reactions. So I have peroxide to water, and then I have iron 2 plus to iron 3 plus. Now I don't have anything other than hydrogen and oxygen to balance. Down here, I have 2 oxygens on the left and I have 1 on the right. We balance oxygens by adding water, but obviously water and water are the same thing, so we can just put a 2 right here. Now I have 4 hydrogens on the right, but only 2 on the left, so I'm going to add 2 hydrogens. And now the iron, those are balanced, and I don't have any oxygens or hydrogens. So now I need to use my electrons to balance charges. Up here I have +2 on the left and no charge on the right. So I'm going to add 2 electrons to balance that out. On the bottom I have +2 on the left and +3 on the right. So I'm going to add an electron to the right to balance that out. Again, so my top reaction is my reduction reaction. My bottom reaction is my oxidation reaction. Now I have 2 electrons at the top and 1 at the bottom, so I'm going to have to multiply through by 2. Now my electrons cancel, and I have no other like terms, so I'm going to add the 2 together. So I have 2H plus H2O2 plus 2 iron 2 pluses yields 2 iron 3 pluses plus water. And after we do all of this work, we can always go back and check and make sure everything adds up. So on the left-hand side, I have 4 hydrogens. I have 4 over here, so that's balanced. I have 2 oxygens, and I have 2 irons and 2 irons. So all my elements are balanced. Now let's look at our charges. 2 times +2 is +4, plus 2 more is +6, and on the right-hand side, I have 2 times 3 plus, which is +6. So my elements are balanced and my charges are balanced. So just another kind of common sense check that you can do once you've got your balanced equation. All right, we're doing another one in acidic solution. So first I'm going to write my half reactions. All right, so first thing we do is we balance anything that isn't hydrogen or oxygen. The manganeses are balanced, but the iodines are not, so I'm going to put a 2 right there. Now I got to balance oxygen with water. I have 4 on the left, so I'm going to add 4 waters on the right. That gives me 8 hydrogens, so I have to balance that with 8 H pluses on the left. So then now I have to balance my electrons. I have plus 8 minus 1, so I have a total of plus 7 on the left. On the right, I have plus 2. So that means that I need 5 electrons on the left to balance out that plus 2 charge. Now on the bottom, I have minus 2 on the left, but I have 0 on the right, so I need 2 electrons on the right. Again, that makes sense. And the top one is our reduction reaction, and the bottom one is our oxidation reaction. Well, 5 and 2 are not equal. We need those electrons to be equal. So we're going to have to multiply the top by 2, and we're going to have to multiply the bottom by 5. So that's going to give me 10 electrons plus 16 hydrogens plus 2 permanganates makes 2 manganese plus 8 waters. So I multiply the top by through all the way by 2. The bottom one I'm multiplying through by 5, so that gives me 10 iodines, making 5 I2s plus 10 electrons. Now I'm going to cancel out any like terms. My electrons have to cancel or I've done something wrong. Excuse me. That's the only thing that cancels for this one. So I have 16 hydrogens plus 2 permanganates plus 10 I minuses yields 2 manganese ions plus 8 waters plus 5 iodine. Again, real quick, let's do our common sense check or add up to make sure our elements balance. So we have 16 hydrogens on the left. We have 8 times 2, we have 16 on the right. We have 2 manganese on the left. We have 2 on the right. We have 4 oxygens on the left. We have, 4 times 2, 8 oxygens on the left. We have 8 on the right. And we have 10 iodines on the left and 10 iodines on the right. Now let's look at our charges. We have plus 16 minus 2 minus 10. So that leaves me with plus 4 on the left. And then I have 2 times plus 2 is plus 4 on the right. So my elements are balanced and my charges are balanced. Last example, this time we're going to do it in basic solution, which means we do everything the same except at the very end we convert acid to base. So I have my 2 half reactions. And then I'm going to balance anything not oxygen or hydrogen. Those are already balanced. So now I'm going to balance oxygens by adding water. So I need to add 1 water on the left. That gives me 2 hydrogens, so I need 2 hydrogens on the right. Down here, I'm going to have to add 5 waters because I have 5 oxygens on the left, and that gives me 10 hydrogens that I need to add. So now I have to balance with my electrons. I have no charge on the left of my first reaction, but I have plus 2 on the right, so I got to add 2 electrons. And then on the bottom, I have no charge on the right, but I have 10 positive 10 on the left, so I'm going to have to add 10 electrons. So in order to make my electrons balance, I'm going to have to multiply this through by 5. That gives me 5 waters, 5 carbon monoxides, 5 carbon dioxides, 10 hydrogens, and 10 electrons. So now I'm going to cancel out my like terms. Electrons have to cancel. I have 5 waters, 5 waters. I have 10 hydrogens, 10 hydrogens. And you know what? because my hydrogens canceled, I don't even have to convert acid to base because I already canceled out all of my acids. So 5 carbons, 5 carbons, 5 plus 5 is 10 oxygens, 10 oxygens, 2 iodines, my charges are 0 and 0. So this is balanced. So that was kind of a silly example. So let's actually do one more so we can actually see it in basic solution. So we are going to balance this equation in basic solution. So we still start with the same steps of splitting it into the half reactions. Balance anything that isn't hydrogen or oxygen, and my manganese is and my sulfur is already. So now I have to balance these oxygens. I have 4 on the left, I have 2 on the right, so I'm going to add 2 waters, which gives me 2 times 2, 4 hydrogens, so I'm going to add that on the left. The bottom, I have 3 oxygens on the left and 4 on the right, so I'm going to add 1 water on the left to balance that oxygen, which gives me 2 hydrogens. I'm going to add 2 on the right. So now in the top reaction, I have 4 plus minus 1, so I have a total of plus 3 on the left, and I have 0 charge on the right. So I've got to add in 3 electrons to balance that out. In the bottom reaction, I have minus 2 on the left, and on the right, I have minus 2 plus 2, which is 0. So to balance that out, I need 2 electrons on the right. So in the top reaction, I have 3 electrons. In the bottom reaction, I have 2. So in order to make those equal, I'm going to have to multiply the top reaction by 2, the bottom reaction by 3. So that changes 3 electrons to 6, 4 hydrogens to 8, 2, 2, and 4. My bottom reaction, that changes 3, 3, 3, 6, and 6. So now I'm going to cancel out any like terms. Of course, my electrons have to cancel. I have 3 waters on the bottom. I have 4 on the right. So 3 of those are going to cancel, which is going to leave 1 water on the top. I have 8 hydrogens on the top. I have 6 on the bottom. So 6 of those are going to cancel, which leaves me with 2. So now let me combine my 2 reactions. So now I've combined my 2 reactions, but the question said for us to do this in basic solution. So I got to convert this hydrogen into water by adding 2 hydroxides, which makes 2 waters. Well, if I added 2 hydroxides on the left, I have to add 2 hydroxides on the right. I can't just add them out of nowhere. So now I have 2 waters on the left, I have 1 on the right, so then one of those cancels out. And now my overall reaction is 1 H2O plus 2 MnO4 minus plus 3 SO3 2 minus 2 MnO2s plus 3 SO4 2 minuses plus 2 hydroxides. So notice we are left with hydroxides, which is balancing it in a basic solution. And just like we did before, we can make sure all of our elements and charges are balanced. So in the left-hand side, I have 2 hydrogens. On the right, I have 2 hydrogens. On the left, I have 1 plus 8 is 9, plus 3 times 3 is 9, so I have 18 oxygens. On the right, I have 2 times 2 is 4, plus 12 is 16, plus 2 is 18 oxygens. 2 manganese, 2 manganese. I have 3 sulfurs and 3 sulfurs. So all my elements are balanced. Now let's look at the charges. I have 2 minus, so 2 minus, so minus 2. 3 times minus 2 is minus 6, so I have minus 8 total. And on the right, I have 3 times minus 2, which is minus 6, plus minus 2 is minus 8. Elements and my charges are balanced. Thank you for sticking with me for almost 45 minutes. I'm sorry it's so long. See you guys next time.